Hello everyone. In this video, we will learn the technique to integrate any functions of the form tan to the power any number times secant to the power an even number which is not zero. So 2, 4, 6, and so on. Okay. So, for example, the first thing that happens here is integral of secant squared. The power of tan can be 0, and then secant squared. Then what we already know that the derivative, so let me just put this as a point that we already know, the derivative of tan x is equal to secant squared x, or in other words, the differential form is that secant squared x dx is this. Well, as a result of that, or these are basically equivalent things to say, integral of secant squared x dx is tan x plus c. So that covers the first case, but this is important for us because we will try to use the fact that we can always separate a even power secant to the power 2 factor in these integrals and generate derivative of tan x. And you see that where we are going. So then the key point here would be apply u equal to tan x substitution. Okay, let's do this in an example and see at least the first example we have here. So tan to the power 3x, this can be any power, and secant x dx, secant squared. So that is even one, and that's where we see that, oh, see, this is derivative of or differential of tan x. So that is a good sign for us. Use substitution, setting u to be tan x. As a result of that, du is going to be what? Secant squared x. Well, with that, then we have du here. Well, this is tan to the power 3. This is just u to the power 3. So we can easily transfer our x integral to u integral. And that will give us u to the power 404 plus c. Well, we are not done because we have to plug in back the original function tan x into u. So this will be 104 tan to the power 4x plus c. Well, here what we have, the take home note is that we can always, in these integrals, note that we are saying that secant has enough power. It's even, not 0. So it means that you can always take out the factor, separate the factor secant square x factor to generate du when we set u to be equal to tan x. Okay, let's do this example, the second example here. So we will go exactly the same way. Yes, tan to the power 3x secant to the power 6x dx. What do I do here is that, okay, first take out power two powers of secant and write it separately. Why do we need that? Because if you use u substitution, let me do this one with the black one, u sub, then we have u equals to tan x will always generate the same du. Yes, secant squared x dx. So this is my du. This is u to the power 3. How about secant 4? I have to write secant 4 in terms of tan. Well, here the key identity that we have is that, well, this is the identity we have been using for the other one with just small change in order. I took 1 to the other side. So this way we have, well, basically secant to the power 4x. I can write it as, well, let me do that part there. So the key point here is that identity. And now I can write this guy. This is tan to the power 3x. See, secant square to the power 4, I can write it as secant square to the power 2. But secant square inside the bracket, I can replace it by tan squared x plus 1. That is the identity I'm using. And then I have secant squared x dx. Now that everything is in terms of u, that part is going to be du. This is u squared plus 1 to the power u, and that is u to the power 3. So I have now u integral waiting for me to just turn everything to u integral. Oh, but let me just expand this one as well here. So u squared plus 1 to the power 2 is u4 plus 2u plus 1 du, and that integral is just u to the power 7 plus 2u to the power 4 plus, I missed 2 there. Now I'm happy that I caught it at this point. So this is u to the power 3 du. Integrate, just simple power rule would do the job. Linearity and power rule do the job. So it will be u to the power 8 over 8 plus 2 over 6 u to the power 6 plus u to the power 4 plus c, and then plugging back everything. So instead of u, we have tan. So 1/8 of tan to the power 8x, 1/3, 2 over 6 is 1/3, tan to the power 6x plus u, where did I leave that 4? Okay, so I have to be careful with the numbers, and that is my integral. And well, from this example, you see that the second point that we should keep in mind is, well, we have use the identity secant squared x equals to tan squared x plus 1 to write the remaining powers. We take out 2 powers of secant. The remaining powers is still even. We can turn these ones in terms of tan x. Okay, so that way we are done, and this example gives us the last tool that we wanted to have. Okay, very nice. Let's move and do one more example. So I have find the volume of the solid of revolution obtained by rotating the region under the graph of tan to the power 10x secant x on the interval 0 to pi over 4. To be honest, I don't need to know what kind of graph this guy has. The only thing I have to care about at this point is just this function is positive and starts from 0 at pi over 4. It's somewhere here. It's root 2. The shape, I don't know what would be the shape, but yes, I'm assuming something like that would be what we're looking for. Okay. Now the region, this is pi over 4. The region is this piece here. We start rotating it about x-axis, and what we get is this nice You see, I can draw nice pictures. Okay. But the point is that for these things, the volume of the revolution in this case would be pi integral 0 to pi from a to b f of x squared. So remember, this thing comes from the fact that the cuts we made we make slices we make are cylinder, and the radius is f of x. So pi r squared is where this pi comes, and f of x squared is the area of the base, but the height here is just, or thickness is dx. So that is what we have. That was a crash course on how to find the formula for the revolutionary items of revolution. Okay, so in this case we have pi go from 0 to pi over 4, tan to the power 10 squared tan 20x times secant x, well, squared. That is what we have. Okay, pi f of x squared dx. Now I have, well, secant x squared there, so u substitution can be applied right away. So u is tan x, so that the u will be secant x, secant squared x dx, and since this is a definite integral, we have to change the limits as well. So this will be tan of 0 is 0, and tan of pi over 4 is 1. Now my x integral can be easily transferred to u integral, and this will be u to the power 20 du, and that's just a simple integration rule. This will be 21 over 21, go from 0 to 1, and if you plug in 1 you get 1 over 21, and if you plug in 0 you get 0. So the volume of that object is going to be pi over 21. Well, this gives me all the tricks I needed to know for this kind of integrals. Let's just cover, let's quickly see the summary. Well, the first step is that you have to take out a factor secant squared x to generate du, and then the remaining part will be an even power again. Because it was even power, we took out 2 of that, that's even. We can rewrite it as this way and apply the identity which is here and write that piece in terms of tan x, and then everything is ready to u integration. So you turn it into an easy integral. Well, it's going to be sometimes not very easy, but this will be something that you can apply. If n is small, you can expand and find it. Sometimes using substitution, you can find it, and so on. So it will be something easy, much easier to handle than the original integral. Okay.